be perfect. Okay, so welcome to Practical Astronomy. We are focusing on celestial navigation tonight. It is quite heavy. There's going to be a lot of terminology and jargon that we use in astronomy, so if you're not used to it, or this is your first time, I see a lot of new faces. It can be a little bit intense, but don't worry. We'll step it up and make it a little bit more intense at the end of it with a quiz, which you'll be doing on your phone online. I will give you the password to the Wi-Fi here, and then you can compete with each other for no prize at all. So it's going to be great. I wanted to start off with just giving you a little bit of context as to why celestial navigation and why it is also quite important. A lot of our sort of ancestors back in the day spent a lot of time outside looking at the stars, and I feel like we don't spend as much time observing it or appreciating the stars that we have at the moment, and so we sort of tend to lose that sort of connectivity with time and beauty that I'm hoping that we can get back, especially now that you guys are all here with the Astronomical Society. Here is an image of what, there are lines, but our ancestors would not have seen these lines at all. They would have just seen stars, these bright dots appear to move in the sky for them. If they noticed and they stayed out there for long enough, they would have seen the motion of the stars across one night. And the thing is, for them, this was their way of telling time. It was a very important way for them to keep track of seasons and days and months, and it told them when they should plant, harvest, a lot of things to do with astronomy told them when they have to wake up, when they have to go to sleep. So a very important tool for them. But the thing was, because they were just random stars, they had to group them up and create these constellations or find these patterns that they could see repeatedly over a period of time, so that they knew, this particular group of stars is up at night now, which means possibly winter's coming. I don't know, Game of Thrones thing there for those of you that are interested. Anyway, so this is just a little bit of our constellations. Back in those days, in those times, I can imagine we had no scientific background, we had no knowledge of what was going on. So for them, the entire night sky or the entire universe sort of was just surrounded around them. So this is what we call a geocentric view of the universe, which means we're right there in the middle as Earth, and everything goes around us. And to them, that was true, because for them, the stars appeared to move, the sun appeared in one spot, and then set in another spot. Everything appeared to move, and for them, their only constant was where they were standing, the Earth. And so for them, that was the center, and everything else just appeared to move around. So this was sort of our old school way of looking at how the universe was. Well, we know that's not really the case. We go around the sun, which we then thought was going to be the center of our universe, and then we discovered it's actually just some insignificant glowing ball on the edge of a galaxy in the middle of just a whole bunch of other galaxies. So, we're like insignificantly significant, I guess. So that's like our old school view of looking at it. And then, I guess, this is sort of what they would have seen over a period of night as they were observing the sky. This was footage taken by a friend of mine, and she was based out in Timpo, and this is just how you would see the night. If you spent enough time, this is how you would see the night sky sort of progress over, a couple of hours, maybe like 4 or 5 hours. And you would start to see things appear, start to see things disappear. And there was a lot of beauty around that, as you can tell. And it was a very important way for them to tell time. So a lot of astronomy is for us to be able to tell time and to tell our position, and that gives you a lot of information. information, but for them, they didn't have any of that. So how did we start to figure out this aspect of time? How did we try to make sense of it all? I'm going to show you sort of just start you off with the basics of just day and night. So when the sun is up, it's daytime. When the sun goes away, it's nighttime. That's how we have a concept of the day. For those of you that know a little bit more, you would say, oh, it's how long it takes for the Earth to spin once. That is a day. Now, if you want to take it a step further, you would say, okay, the Earth is spinning once, according to whom? Relative to whom? What are you basing this spinning on? Because the Earth doesn't just spin, it spins and it moves at the same time. So how do you go about figuring out that sort of aspect of it? So I'll show you a quick video, and this will kind of give you an idea of what a sidereal day is. So this is sort of the first term we're coming across. And this is what a sidereal day is. A sidereal day is when you look at stars that are really, really far away, and you assume that they are fixed. Right? So the Earth is moving, the sky isn't moving. Remember, everything that you see moving in the sky is a reflection of the Earth's motion. Everything in the sky, for all intents and purposes, stays still. We're the ones that are moving. Technically, that is not true, because everything is spinning, everything is moving, nothing is actually still in the universe. But we kind of have to assume that you've got these distant stars that are really far away, they're fixed, and that is going to be my anchor, and then I'm going to use that as a point to say, I'll come around once, and if I see those same stars again, I've gone around once. So that's going to be a day, and hopefully it works. So you can see that. So we have one rotation from the meridian, and that takes about 23.9 hours. So it's about 23 hours and 56-ish minutes. Okay? That's a sidereal day. The thing is, it's not as simple as that, because you might be wanting to use these distant stars, but there is another star a lot closer to us that has a bigger effect, the sun. So how would that then look? Did I take that one? Yeah. So we'll see if we can show you that one there. So this is your Earth's motion. This is the sun. And that red line that you're looking at, that's your prime meridian. And if we were to take the sidereal day, that's where it would stop. The thing is, it sort of has to swing a little bit further back, or a little bit further more forward. And that extra part of it, that's what we call a solar day. Alright, so this is like 24 hours. So a sidereal day is when you don't have that green line, you use that fixed motion of the stars, but if we're taking the sun into consideration and the fact that we're spinning and moving at the same time, you get the full day. So this is the day that we actually use as part of our whole sort of system. So this is the solar day that we use. Still going? Alright. And that's really important, because when you start to now come out into the nighttime, and you want to see what it looks like for an entire night sky going through, you get to see these beautiful star trails if you sort of keep taking photographs every so often, and then you stack them one on top of each other, and you can actually see the sky moving, and you can see that spinning effect going. Now for us here in New Zealand, we've got a really beautiful south celestial pole that we can see quite clearly very high above, and that point there is fixed, and everything else seems to move around it. The closer you are to that point, the smaller your movement, the further away you are from that point, the bigger your movement. Okay? So that is our fixed point that we use to refer to. It's called our celestial pole, so another term. And then coming back into that, I'll show you some pictures and diagrams around it. So this is your idea of a day, right? This Earth's rotation around its axis. Either you take it with reference to distant stars, or you take it with reference really see it day to day. It's really slow moving, but you can sort of you can see the effect of what a year would do over a longer period of time. Say a month, 2 months, 3 months, you can really see the effect of it. But in order to do that, you kind of have to sort of go outside and stand and actually make an observation and know what the sky looks like. Say you go out at 8 o'clock and you look at it. So say you do go out at 8 o'clock and you look at just one star or one particular point in the sky, you look at where it is. If you look at it the next night, it's pretty much going to be in the exact same spot, according to you, at that same time. There's not going to be much of a difference. All right? Over several nights, you might notice that there will be a little bit of a jump. All right? If you come back to that same point after a month, now you're going to see a significant jump in that position of that star. All right? If the Earth was just spinning in one spot, then you would just say every star would rise and set at the same time and your sky would not change at all. Right? That was what you would expect. That was what you would expect if we were just moving around on the same axis. Not the point. For a year, we move around an entire sort of orbit around the sun. And so the sky around us also appears to change. And that's a change that you can see very slowly, where you have to take that effect. You have to take the effort to go outside and actually see the sky changing over a long period of time. And then you can see the effect of what the sky would look like over a period of a year. So one revolution around the sun, 1 year. And that brings a lot of changes and effects to us in terms of seasons. Now we see it like locally with the changing of the air temperatures, the leaves change, blah, blah, blah. But here's a really nice image I saw where you can see the effect of the season on a global scale, where you can actually see how summer and winter sort of fluctuate over the northern hemisphere and the southern hemisphere, which is actually quite neat because it actually looks like the Earth is breathing at a certain point, and that's quite nice. Now, if we look at it in an astronomical perspective, right, this is what we're looking at. We have the Earth moving around the sun over a year. This is a very exaggerated elliptical orbit, by the way. We have a very nearly circular orbit around the sun. For you to just see what the difference is, this distance here, from our furthest point away from the sun, we call that the aphelion, in this case, apsis. It's only 152 million kilometers away, whereas our closest point at perihelion to the sun is 147 million kilometers away. So that's supposed to only show you a 5 million kilometer difference, but slightly exaggerated so that you can see what's happening. So over the course of the year, there's certain times that we move around the sun faster, and certain times of the year we move around the sun a little bit slower, using Kepler's laws. We don't have time to go into that. And then there's parts of the times where we have things called equinoxes and solstices. Equinoxes and solstices just sort of show you where the sun is hitting the Earth, for how long, and what parts of the Earth is getting how much light. And in order for you to see that, you've got to sort of take the Earth in this sort of perspective and see if we were at equinox, so that happens twice a year. So for us, that is in September and March. That is when the rays or the light from the sun hits directly over the equator, and we get equal amounts of day and night-ish. And we just get this huge spread of light. Okay? So that's the equinox. But for a solstice, this is more pronounced during our summer and winter time. So in this case over here, the northern hemisphere, because of the tilt of the sun, tilt of the Earth, sorry, the northern hemisphere is tilted away from the sun, so they're going through winter. And for us here in the southern hemisphere, we're tilted towards the sun, so we're going through summer. So as you can tell, we're getting a lot more light concentrated on this area here around the top of Capricorn, whereas in the northern hemisphere, they're not getting as much concentrated light. And they will still be able to get their summer when the Earth sort of takes an entire rotation around and comes back onto its opposite side. And then when you get that, you can see that at this point over here, the northern hemisphere gets their summer, southern hemisphere gets their winter. So it has nothing to do with, so seasons don't really have to do anything with our rotation around the sun. It has to do with the rotation and the fact that we're actually tilted slightly on our axis. So we're not sort of up and down and spinning. We're off slightly by about 23.5 degrees. And because of that, we get this really cool effect of seasons coming in and out. Now remember, 5 million kilometers of difference between here and there doesn't make that much of a difference. But if you do have a look, the southern hemisphere is pointed towards the sun. So technically, we might be getting slightly hotter summers, but I'll have to go and check on that.
Slightly shorter as well.
Yeah.
We lose about a day of summer versus the northern hemisphere because the Earth is travelling faster.
We move faster in this area and slower in this area, just because of the way it spins around. Alright. Now, it's really important that we understand the concept of time and how things work, and that globally we agree to it as well. So I have a story which is quite interesting to do with this picture over here. So I think Julius Caesar was trying to clean up the calendars that we had, which was the Roman calendars, and their days for a year was somewhere between 355 days and 378 days for a year. And so Julius Caesar came along, created the Julian calendar, and he sort of cleaned it up, and he said 365 and a quarter, and that's going to be a year. And then a little bit later on, there was another guy that came along. His name was Pope Gregory the 13th, and he refined the calendar system a little bit later on. Now this was back in the 1500s. And there wasn't a lot of difference between the Julian calendar and the Gregorian calendar. Apparently I've been told it's like 10 minutes of a difference between those two. But here's where it gets interesting. So remember, that calendar system was sort of introduced in the 1500s, and most other countries had switched to the Gregorian calendar system, except for Russia. In fact, this is a photo of the London Olympics in 1908, where because Russia didn't switch to the Gregorian calendar till 1912, they turned out to be Olympics 12 days late. So when your calendar systems don't align by 10 minutes over a long period of time, it makes a difference. And so I think we're all now using the same Gregorian calendar system, and things are dandy. But that's a little interesting story for you to sort of take away. I've got another video, a quick little snippet to show you, just to show you the exposure of light on the Earth. So the Earth itself is not tilted, so it's slightly misrepresented. The Earth itself is not tilted. What you're looking at here is like sort of the coast of Africa, and you can see Madagascar here. And you can just see how much light each sort of hemisphere is getting over the course of the year, and how that is shifting through summer, winter, solstice, equinox. So you can just see that, which is quite cool, but you've just got to keep in mind that in this case here, the Earth is still, and we're just shifting the amount of light that you're getting in there, which is quite neat. Which brings me to this. Is that all I need to know?